Hello friends, welcome to the next episode of mass transfer operations. And in this particular segment, we are going to discuss about the laminar flow and boundary layer conditions in mass transfer operations. So let's have a brief outlook that what we discussed in the previous lecture. We discussed about the mass transfer coefficient in the previous lecture, then different type of mass transfer coefficient. Then we discussed about the equimolar counter diffusion in two components. We established the relationship between the mass transfer coefficient and we discussed about the mass transfer coefficient and film thickness. Apart from this, we discussed about the dimensionless numbers in mass transfer operation. In this particular segment, we are going to discuss about the mass transfer coefficient in laminar flow. We are going to discuss about the mass transfer in falling film. Apart from this, we will discuss about the laminar falling film in inclined surface. We will also discuss about the mass transfer coefficient in turbulent flow. Apart from this, we will discuss a boundary clear theory and film theory. All these things we are going to discuss in this particular section. Now, let us talk about the mass transfer coefficient in laminar flow. In principle, rather we don't need to study the mass transfer coefficient in laminar flow condition. A uniform method dealing this both laminar flow and turbulent flow is nevertheless desirable. So, we shall choose one relatively simple situation to illustrate the general technique and to provide some basis for considering turbulent flow. Now, this is the particular figure. This particular figure shows a liquid falling in a thin film in a laminar flow and down a vertical flat surface while being exposed to a gas A, in that case which dissolved in that particular liquid. So, this is a very common phenomena when a gas is usually dissolved in a particular liquid, like in a scrubbing operation. So, this liquid contains a uniform concentration of Ca, not of A at top. At the liquid surface, the concentration of the dissolved gas is Ca1. In the equilibrium with the pressure A in the gas phase, now since Ca1 is greater than Ca0, gas dissolves in the liquid. The problem is to obtain the mass transfer coefficient Kl, with which the amount of gas dissolved after the liquid falls a certain distance L. This can be computed. The problem is solved by the simultaneous solution of equation of continuity for the component A with the equation which usually describes the liquid motion in the Navier-Stokes equation. The simultaneous solution of formidable set of partial differential equation becomes possible only when several simplifying assumptions are made. Now, let us consider this particular equation which is derived for unsteady state mass transfer. Here, Vx del C over del x plus Vy del Ca over del y plus Vz del C over Ca over del z plus del Ca over del t is equal to dAb, del 2 Ca over del x2 plus del 2 Ca over del y2 plus del 2 Ca over del Z2 plus Ra. This is the equation number 1. Now, for the present purpose, assume that there is no chemical reaction within the system. So, we can take Ra is equal to 0 and condition do not change in the x direction perpendicular to the plane of the paper. All derivatives with respect to x should be 0. Now, if we take the steady state condition prevails, in that case del Ca over del T is equal to 0. Now, we can take the other assumptions too. One is that the rate of absorption of gas is very small. This means that Vz in equation 1, this is the equation 1, and due to the diffusion of A is essentially 0. A diffusion of A in the y direction is negligible in comparison with the movement of A outward due to bulk flow, and that is dAb del 2 Ca over del y2 is equal to 0. And the physical property is in this case, that is dAb rho mu are constant. So, the equation 1 this equation can be reduced to Vy del C over del y is equal to dAb del 2 Ca over del Z2, and we can say that this is the equation number 2. Now, if we talk about the mass transfer in falling film, now this states that A added to the liquid running down at any location z over an increment of in y. So we have to be the diffusion, we have to be called as the diffusion in the z direction, and the equation of motion under this condition can be reduced to mu del 2 Vy over del Z2 plus rho g is equal to 0, and that is the equation number 3. Now the solution of equation 3 with the condition Vy is equal to 0 at Z is equal to delta, and that dV over dz is equal to 0 at z is equal to 0 is well known, and this can be represented like this. Vy is equal to rho g del 2 over 2 mu into 1 minus z over delta to the power 2, and that can be represented as equation number 4. So, the maximum velocity which occurs at z is equal to 0 in this particular equation, Vy max is equal to rho g del 2 over 2 mu, and that is equation number 5. So, the bulk average velocity, this can be obtained like Vy average. This can be represented as a mathematical formula like this, and Vy average can be represented if we adopt all kind of integration and other thing. This can be put as rho g del 2 over 3 mu, and this can be written as equation number 6. So, the film thickness can be represented as delta is equal to 3y average mu over rho g to the power half, and that is equation number 7. So, if we substitute the equation 4 into equation 2 which we derived previously, and then by equation 6 we get this final equation 3 over 2 Vy average into 1 minus z over delta to the power 2 del c over del y is equal to dAB del 2C over del Z2. So, which is to be solved under the different conditions, like at Z is equal to 0, CA is equal to CAI at all the values of Y, and at Z is equal to delta. Del CA over del Z is equal to 0 at all the values of Y, since no diffusion takes place into the solid wall. And at y is equal to 0, Ca is equal to Ca naught at all values of z. So, the solution in the result in the general expression, an infinite series gives Ca for any z and y. Therefore, the providing the distribution that Ca z at y is equal to L. So, if we take equation 4 and 5 into consideration, then Vy is equal to Vy max 1 minus z over delta, where Vy max is equal to 3 by 2 Vy average. So, if the solute is penetrated only a very small distance into the fluid, and that is a short contact time, that is T is equal to V over Vy max, then the solute A that has diffused, this has been carried out along with the velocity Vy maximum. So, the previous equation 2, this becomes del Ca over del y over v is equal to dAb del 2Ca over del Z2. This is equation number 9. So, if we use Ca is equal to 0 at y is equal to 0, and Ca is equal to Cai at z is equal to 0, and Ca is equal to 0 at z is equal to infinite. So, if we integrate equation 9, then it can be, this is equation 9, if we integrate, then Ca over Cai, this is equal to Fc over Z 4 DAB Y over VY. This is equation number 10. Now, where this particular is a complementary error function of y, it can be written as ERFCY is equal to 1 minus ERFC. Y are the standard tabulated functions. So the local molar flux at the surface Z is equal to 0 at any position y from the top of the entrance can be given as NA is equal to minus DAB del CA over del Y. Z is equal to 0, and this can be CAI in DAB VY over tau Y. This is equation number 11. So the total mole of A transferred, total mole of A transferred per second to the liquid over the entire length y is equal to 0 to y is equal to L, where the vertical surface is unit width which can be calculated like NA L into 1 0 to T NA Z is equal to 0 dy 0 to L CAI DAB Y VY maximum, which we are targeting, to the power half into 1 over y to the power half dy, which is equal to L CA 4 DAB VY pi L to the power half. This can be written as equation number 12. Now let us take up a problem. The absorption of pure carbon dioxide is carried out at 1 atmosphere pressure and at 25 degrees centigrade by using water film flowing down a vertical wall of 1 meter long, and the water is essentially CO2 free at the outset. The average velocity of the liquid is 0.2 meter per second, and the solubility of carbon dioxide in water at 25 degrees Celsius and 1 atmosphere is, that is CAI initially, is equal to 0.336 kilomole per meter cube. So you need to calculate the film thickness and the rate of absorption of carbon dioxide. Now some statistical information is given to you, like the DAB is equal to 2 into 10 to the power minus 9 meters square per second, and the solution density is equal to rho is equal to 997 kilogram per meter cube, and the viscosity, which is foremost important to solve this particular problem, is given as 8.95 into 10 to the power minus 4 kilogram per meter second at 25 degrees Celsius. So let us solve this particular problem. Now it is given that Vy average, this is equal to 0.2 meter per second. P is equal to 997 kilogram per meter cube. Mu is equal to 8.95 into 10 to the power minus 4 kilogram per meter second, and G is 9.81 meter per square. So delta is equal to 3V average mu, this is the standard formula which we discussed earlier, rho G to the power half, and this is 3 into 0.2 into 8.95 into 10 to the power minus 4 over 997 into 9.81, which is equal to 1/2. So delta is equal to 2.34 into 10 to the power minus 4 meter. So now CAI is given to you, that is 0.0336 kilomole per meter cube. DAB is given to you 2 into 10 to the power minus 9 meter square per second. Length is given 1 meter. So NA is equal to CAI for DAB Vy max tau L to the power half. So if we substitute all these values, then it becomes Na is equal to 0.0336 into 4 into 2 into 10 to the power minus 9 into 0.2 tau 1 to the power half, and this comes out to be 7.58 into 10 to the power minus 7 kilomole per meter square second, and this is our required answer. Now let us talk about the laminar falling film in inclined surface. Sometimes this inclined surface play a very vital role in this aspect. Now this is our inclined surface at angle theta. So any liquid flowing down a surface, a velocity profile which is usually established with the velocity increasing, let us say from 0 at the surface itself to a maximum where it is in contact with the surrounding atmosphere. So the velocity distribution may be obtained in a manner similarly what we used in connection with the pipe flow, but the driving force is attributed to the gravity rather than the pressure gradient. So for the flow of liquid of the depth of say delta down a plane surface with the width w, which is inclined at an angle of theta to the horizontal. So a force balance in the y direction parallel to the surface may be written in this particular aspects. Now in an element of length dy, the gravitational force acting in the part of the liquid which is at the distance greater than z from the surface, this can be written as delta minus z into w dy rho g sine theta. Now if we talk about the drag force, so if the drag force of the atmosphere is negligible, the retarding force for laminar flow is attributable to the viscous drag in the liquid at a distance y from the surface, and that is equal to mu dy over dz w dy. Now where vy, this is the velocity of the fluid at the position, and therefore the equilibrium, thus the equilibrium we can write delta minus z into w dy rho g sine theta is equal to mu dvy over dz w dy. Now since there will be normally no slip between the liquid and the surface where Vy is equal to 0 when Z is equal to 0. So we can write the integration like from 0 to Vy, dVy is equal to rho g sine theta over mu and 0 to Z delta minus Z into dz, which can be modified to Vy is equal to rho g sine theta over mu into delta z minus 1 over z square. So the mass rate of the flow, that is the m of the liquid or mass of the liquid down to the surface, can be calculated as dot m is equal to 0 to delta rho g sine theta over mu into w delta z minus 1 over 2 z square into rho z, which can be, after simplification, it can be written as dot m is equal to rho square g sine theta over mu into w into delta 3 over 2 minus delta 3 over z, and which can be further modified to this final shape. Now, if we talk about the laminar falling film in an inclined surface, so average velocity of the fluid can be represented as Vy average is equal to dot m over rho w delta is equal to rho g sine theta delta square over 3 mu, and for vertical surface sine theta is equal to 1. So the equation can be modified as V is equal to rho g delta square over 3 mu. The maximum velocity which occurs at the free surface is given by Vy is equal to rho g sine theta delta square over 2 mu. And this is almost 1.5 times the mean velocity of the fluid. Now let us talk about the boundary layer theory in mass transfer. The exact solution can be obtained for the hydrodynamic boundary layer for isothermal laminar flow usually past a plate. Now this is the typical laminar flow of a fluid passes a flat plate. This is the flat plate and the concentration boundary layer. So at this level this is Ca. Now an extension to the Blasius solution, this can be extended to derive an expression for the convective heat transfer. Now in the analogous manner, we can use the Blasius solution for convective mass transfer as well as the same geometry and laminar flow. Now here Ca infinite is the concentration of A in the fluid approaching the plate. Now Cas, that is the concentration of A in the fluid adjacent to the surface. So in other words, we can say like this. So if we start with the differential mass balance and simplifying it for steady state process where del C over del T is equal to 0. Now flow only direction, flow in the direction of x and y. So if so Vz is equal to 0 and neglecting diffusion in x and z direction, so it can be given as Vx is into del C over del x plus Vy into del C over del y is equal to dAb del 2 Ca over del y2, and this is can be represented as equation number 13. So the momentum boundary layer is very similar, and therefore this equation can be modified as Vx to del Vx over del x plus Vy is equal to del Vx over del y plus is equal to mu over rho del 2 Vx over del y2, and this can be represented as equation number 14. So the thermal boundary layer, if we talk about, is also similar. So this can be represented as Vx into del T over del x plus Vy is equal to del T over del y is equal to K over rho Cp del 2T over del y2, and this is equation number 15. And if we adopt the dimensionless correct concentration boundary conditions, then at y is equal to 0, the Vx over V infinite is equal to T minus Ts over T infinite minus Ts is equal to Ca minus Cs over C infinite minus Cs is equal to 0. So this can be represented as equation number 16. And on simplification, if we go for y is equal to infinite, this equation can be further modified, which is represented over here. That is Vx over V infinite is equal to T minus T s over T infinite minus Ts is equal to Ca minus Cas over Ca infinite minus Cs is equal to 1. So this is equation number 17. Now the Blasius equation is applied to convective heat transfer. In that case, mu over rho over alpha is equal to Na, which can be represented as 1. Now we use the same type of solution for the laminar convective mass transfer, where mu over rho over dAb is equal to Nsc, that is Schmidt number 1 minus 0, and the velocity gradient is derived in the fluid mechanics, and that is dVx over del Vx over del y at y is equal to 0, that is 0.0332 V infinite over x and Reynolds number to the power half. So where n Re, that is Reynolds number at x V infinite rho mu. This is equation number 18. Now if we recall this equation number 17 here, then Vx over V infinite is equal to Ca minus Cas over C infinite A infinite minus Cas. This is equation number 19. Now if we differentiate the equation 19 and combine the result with the equation 18, then it can be written as dCA over del CA over del Y at Y is equal to 0. This is equal to CA infinite minus CAS 0.332 over x, and that is Reynolds number over half. This is equation number 20. So the convective mass transfer equation can be written as, and also if we relate with the fixed equation, then NAY is equal to KC CAS minus CA infinite is equal to minus DAB del CA over del Y is equal to 0. This is equation number 21. So from equation 20 and 21 we get K dash Cx over DAB is equal to Sherwood number 0.332 n, that is Reynolds number to the power half in x, and this is equation number 22. So the relationship, this relationship is restricted to gases with Schmidt number is equal to 1.0. Now the relationship between the thickness delta of the hydrodynamic and delta C, the concentration boundary layer, where Schmidt number is not equal to 1, is delta over delta C is equal to Schmidt number to the power 1 by 3, and that is equation number 23. Now as a result, the equation for local convective mass transfer coefficient is given as K prime C x over DAB is equal to Sherwood number in the x direction is equal to 0.332 Reynolds number to the power half and Schmidt number to the power 1 by 3, and this can be represented as equation number 24. So we can obtain the mass transfer coefficient Kc prime from x is equal to 0 to L for a plate with B by integrating this particular equation. So this can be the Kc prime is equal to B over BL 0 to L integration Kc prime dx, and this is equation number 25. So we can represent the integration like Kc prime over into L over DAB is equal to Schmidt number is equal to 0.664 Reynolds number to the power half and Schmidt number to the power 1 by 3. Now let us take another problem. A large volume of pure water at 25 degrees Celsius is flowing parallel to a flat surface of solid benzoic acid, where L is 0.244 meter in the direction of the flow, and the water velocity is 0.061 meter per second, and the solubility of the benzoic acid in water is given, that is 0.2948 kilomole per meter cube, and the diffusivity of the benzoic acid is 1.245 into 10 to the power minus 9 meters square per second. You need to calculate the mass transfer coefficient Kc prime and the flux Na given is whatever given, that is mu is equal to 8.71 into 10 to the power minus 4 kilogram per meter second, and density rho is 996 kilogram per meter cube. So let us solve this particular problem. So the Schmidt number, that is NSC, that is mu is equal to rho DAB. This is 8.71 into 10 to the power minus 4, 996 into 1.245 into 10 to the power minus 9, that is equal to 702. And Reynolds number is given by this particular mathematical representation, and if you substitute the value, then it can be into 996 over 8.71 into 10 to the power minus 4, and that is 1.7 into 10 to the power 4. So Kc prime over DAB is equal to 0.664 4 Reynolds number to the power half and Schmidt number to the power 1 by 3. So if we substitute all the values which we calculated and DAB which is given, then Kc prime comes out to be 3.92 into 10 to the power minus 6 meter per second. So if we calculate NA, we have NA is equal to Kc prime x into Ca1 minus Ca2, which is equal to Kc Ca1 minus Ca2. Now, if the solution is very dilute, then this can be represented at Kc prime is almost equal to Kc. Also, initially it is given, the solubility is given 2.948 into 10 to the power minus 4 kilogram mole per meter cube, that is solubility, and Ca2 is equal to 0 for large volume of fresh water. So if we substitute all these values, it 3.9 Na is equal to 3.92 into 10 to the power minus 6 into 0.02948 minus 0. This comes out to be 1.15 into 10 to the power minus 7 kilogram mole per meter. This is our answer. Now, if we talk about the turbulent flow, so there are many theories which attempt to interpret and explain the behavior of mass transfer coefficient, like Nernst given the film theory, and the penetration theory is given by Higby in 1935, and surface renewal theory is given by Danckwerts in 1951. Now, Nernst, the film theory, the Nernst postulated that near the interface there exists a stagnant film, and the stagnant film, which is the hypothetical, since we really do not know the details of the velocity profile near the interface, and the basic concept is that the resistance to diffusion can be considered equivalent to that in the stagnant film of a certain thickness. The mass transfer occur by the molecular diffusion through the fluid layer at a phase boundary, that is a solid wall, and beyond this particular film the concentration is homogeneous, and it is given by CAB. So the mass transfer through the film occurs at a steady state, and flux is very low, and the mass transfer occurs at low concentration. So therefore this can be, Na can be represented like this. Now, steady state mass balance over the elementary volume thickness, if we try to find out at delta Z. So, the rate of input solute at Z is equal to Na at Z, and the rate of output can be given as like this. So, if we take the rate of accumulation is equal to 0, that is the rate of input minus rate of output. Therefore, at a steady state, mathematically it can be represented like this. Now, let us consider that if we go for Z tends to 0, then Na Z at Z minus Na at Z plus Z delta Z over delta Z is equal to 0. So, upon simplification, we can obtain a various equations like dNA over dZ is equal to 0, and then d over dz minus dab dca over dz is equal to 0. So, we can obtain various equations which are useful in due course of time. Now, if we integrate the previous equation which we developed over like equation number 3, then with the different conditions, a different boundary layer condition, that is Ca is equal to Cai when Z is equal to 0, and Ca is equal to Cab where Z is equal to delta. So, we have now mathematically represent like this. Therefore, according to the film theory, the concentration profile in stagnant film is linear, and the molar flux through Na is given by these two equations. So, dear friends, at the outset we discussed about the mass transfer operation in various aspects like falling film, thickness, all those things, and for your convenience we have enlisted couple of references. You can utilize them as per your requirement. Thank you very much.